Interesting.
Okay, let's do a calculation on those numbers then. So what equation are we going to use? Well, this one's in a data booklet. Energy is mc delta T. And then we're going to take the Q that we get from there, the energy, and pop it into this equation to finally get this value. So I'm going to try and do this following all the rules and sig figs and all of that business. Well, first off, even though this is in the data booklet, it still doesn't tell you what on earth it means. So Q is the energy. Why isn't that E like it was in the other equations? Don't ask. M is the mass of what's heated. C is the specific heat capacity of what is heated. And delta T is the temperature change of what is heated. All right then, so let's go through the first one. So mass, the mass of what's heated. What is being heated? Well, you saw me heat up the water. So it's 203 grams. Let's pop that in there, 203 grams. The specific heat capacity, well, that is a problem already because it's got a kilogram there and I was in grams. Oh, so you know what? Let me just turn everything to kilograms, and then the units will work nicely. So I'm actually gonna turn this into kilograms by dividing by 1,000. Specific heat capacity, it's 4.18. That's given in the data booklet. Kilojoules per kilogram per Kelvin. And then the temperature change. And so this is where the rub is. I like to ask this question. Here's the graph of my temperature change. Well, what was it at the beginning of the experiment? Well, it looks like here was where the experiment started. So that's not too problematic. But what's the final temperature? Well, we're going to give you, it's normally multiple choice as well, 4 opportunities to cock this up. First of all, I stopped my experiment here. So is that the final temperature? No, because it carried on heating up. There was thermal lag. Even though I shut off the experiment, it kept heating up. So what about this temperature? Is that the final temperature? No, it ain't. But surely that's the hottest temperature. Isn't that the final? No, 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 no. Notice that on this part here, I allowed it to cool down. So that aluminium can was not a perfect insulator. You can see that the experiment was losing heat all the time. Especially at the end, it's very clear because it's cooling down. So what you have to do is back extrapolate from that to come up with your final temperature. But we're not done. So now I've accounted for the loss of thermal energy, the loss of heat from my experiment. Is this the final temperature? No, it's not. It's still not the final temperature. I hadn't even started my experiment here. I'm just waiting for the thing to reach thermal equilibrium before I can start. The water from the tap might have been a little cold. It might be heating up to the room temperature, just from being in the room. So since I started my experiment here, that's where I need to start the reading from. So this is the final temperature. If I read along to there, that's the final temperature. So let's zoom in a bit more. I would say that's 42.2 is my final temperature, accounting for that extrapolation. So 21.4 degrees C. 21.4 degrees C. I'm going to put Kelvin. Hold on. Aren't I supposed to add 273? And no, it turns out that 21.4 Kelvin difference in temperature is the same as 21.4 degrees C difference in temperature. So no problems there. Let's do that calculation. Let me double check the units here. I've got a Kelvin goes with Kelvin, Kilograms go with kilograms, which just gives me kilojoules. Nice. Okay, so that's the energy from burning that 1.24 grams of ethanol that I did in my experiment. So now we have to standardize that to per mole, and then we can check it in the data booklet. So to work out my heat of combustion, that's what I'm going for, is minus 18 point, my God, how have I got such a short-term memory? 16 kilojoules. And now for the moles of fuel, well, don't forget moles is mass over molar mass. What was my mass of fuel? Taking a look here, well, it's going to be the difference between those two numbers, isn't it? So I've got 1.24 grams, and the relative molecular mass of ethanol is 46.069. So I'm going to divide by 46.069 grams per mole. What does that give me? So minus 674.7, and that should be in kilojoules per mole. Alrighty. Yeah, because that gram cancels with that gram, I've got kilojoules per mole. Let's just be efficient with the sig figs here. Let's go back to the original data and see what we've got. So I've got 3 significant figures there. I've got 3 sig figs there. I've got 3 there, 3 there, and 5 there. So I think what I need to do is go with the least sig fig. So that's 3 significant figures. So I'm going to say that's equal to minus 675 kilojoules per mole. I would always advise you put 3 sig figs in case you're cleverer than the grader and I haven't realized that's what you've done. Okay, that's bits done. Alrighty, so there were some uncertainties in the measurements, and let's see how that plays through to that final answer. So looking at the mass of the fuel ethanol, I'm going to add the uncertainties there to get the uncertainty 0.02. And now to work out the percentage uncertainty, I'm going to take my total uncertainty, perform this simple calculation. So that's plus or minus 1.6%. Alrighty, it's not too bad. Looking at the uncertainty for the temperatures, again, I'm going to add the uncertainties together. Let's calculate that uncertainty. So that's plus or minus 0.93%. Again, not too shabby. Looking at the mass of water, there's another uncertainty there. So let's work out that percentage uncertainty. So that's plus or minus 0.49%. Specific heat capacity of water, I don't know what the uncertainty is there, so I'm not going to worry about that. And the molar mass of ethanol, again, comes with no uncertainties. So my uncertainties are due to the mass of the ethanol, the temperature change, and the mass of the water. So combining those two equations, I'm going to get a delta H equals minus mc delta T over the mass of fuel divided by the molar mass of fuel. Let's see what those uncertainties were. So for the mass, so overall, what you've got to do is you have to add those numbers together, and that gives you the overall percentage uncertainty. But what about the ones at the bottom? Don't you divide these and add? No. You have to add all of those numbers together to get you the percentage uncertainty. So that comes out at plus or minus 3.02%. And according to the IB, you really should have that to 1 sig fig. So plus or minus 3%. Moving back to our original one. So let's say that that's plus or minus 3%. That's the percentage uncertainty. Let me work out the absolute uncertainty. What does that actually mean in kilojoules per mole? So that's going to give me plus or minus 20.241, but the IB likes it to 1 sig fig, so it's going to be plus or minus 20. So my actual value was 675, and you know what? The range could be from minus 655 all the way to 695. And that the reason for that range there, I can blame on my equipment. 3% of any problems that I have, 3% of any errors that I have, I can blame on the equipment. Well, now we need to find out what the actual value is. Hopefully, the difference is less than 3%, and I can just blame the crappy equipment. Scroll. I think it's table 14. I'm sad that I know that. Alrighty, enthalpies of combustion. Ethanol is minus 1367. Wow, we are a long way out there. So let's look at my percent yield. Percent yield is your experimental value over the theoretical value, true value, times 100. So I got minus 675. So that would mean that my percent error is going to have to be a whopping 50.6%. So this experiment is designed to not work, and I have succeeded, and in the sense that it hasn't worked. Then you'd be asked about, well, what went wrong? Okay, so 50.6% error is terrible. What went wrong? Well, here's the equation that we were using. I've used the absolute values for the experimental value and for the theoretical value. Otherwise, it gets a bit confusing what you mean by a bigger number and a smaller number. So this number's too small. Absolutely. So using algebra, that could mean that this number's too small, this number's too small, this number's too small, or this number's too big, or that number's too small. So we've got a bunch of stuff to look at in terms of algebra. Alrighty, so the mass of water, that could be too small. Well, I mean, maybe it was too small. I had 203 grams, and I bet there was some evaporation. I don't think there was much evaporation, and I didn't measure it. It wasn't boiling. So let's say it went down to 200 grams. So it's only going to be quite a small percentage change in the value here, a few percent. So if that is the problem, I would say that that is a minor error. And you could correct it. You could measure the water before and after, take an average of the mass. Specific heat capacity, that's a constant of nature, so that doesn't count. The temperature change of the water, that's your major problem. That's your major error here. So the IB often asks, what's the major error? Even though we tried to extrapolate with the graph, it wasn't enough. So energy was lost. It didn't go to the water. It went somewhere else. So you lost energy to the surroundings. You lost energy to the surroundings. You heated up. You heated up the air. You didn't account for that. You heated up the aluminium. You didn't account for that. How could you fix it? Well, sometimes the IB have accepted you could use screens. You could put up things to block the wind that's blowing the air and blowing the heat away. You could use insulation. You could wrap the can careful about that, though. One of the stupider things I saw when I lived in Thailand was I always used to ask the kids to do the experiment twice. And once, I'm lucky I was paying attention, some kid wrapped toweling all around the can here as insulation. There's the thermometer, there's the water. So that's what I used to think of as double dumb. It's dumb because the heat from the burner cannot get to the water because you've insulated it now. And the bigger problem is that the burner will set fire to the insulation and burn the school down. Wonder what that kid's doing now. So insulation, easier than that, is you can just put a lid on. Maybe there was also incomplete combustion when I turned over incomplete combustion. When I turned over the can, you saw that there was carbon, evidence that not all of the combustion produced carbon dioxide and water. Incomplete combustion. And the other problem was that it was only 96% alcohol, and I'm pretty sure the other 4% was mostly water. So taken together, these problems here account for a lot of that 50%. So that's a major error. Now, all of these things are making the water increase in temperature less, so it's a systematic error. These are making the numbers go in one direction, not in a random direction. So it's a systematic error. Everything I circled there makes the temperature change smaller. So the mass of fuel that I burned was 1.24 grams. Well, that number might have been too big. Maybe I only burned 1.2 grams. So I'm trying to think, how could that have happened? I thought I'd burnt more than I did. Well, what could have happened is maybe some of the fuel evaporated when I was wandering around. Maybe the lid wasn't on tightly and some fuel evaporated and I lost a little bit of fuel. But again, that's only going to be minor. That's just going to be a minor error. Minor error. Molar mass of fuel, well, that's unchanging. It's a constant. What they have asked to do in the past is they asked about the aluminium here. So they asked, work out the energy that went into the aluminium. So it's just the mass of the aluminium multiplied by the specific heat capacity of the aluminium. I hate using C for specific heat capacity. Multiplied by the temperature change of the aluminium, divided by the mass of fuel, and that's divided by the molar mass of fuel. Well, I didn't have the brains to measure the mass of the aluminium, so I looked it up on the internet. So let's say 20 grams, and the specific heat capacity is 896 joules per kilogram. Ugh, an ugly unit that is. Let's find another one. Oh, aluminium. Joules per kilogram. Oh. Kilocalories. Oh, I feel dirty just looking at these. Oh, for the love of God, there must be something here. Calories per gram. What is this? The 1920s? Aluminium. All right then. So I see 0.9 for aluminium here. 0.9. So my mass of aluminium is 0.02 kilograms. 0.9. I'm down to 1 sig fig already. Kilojoules per kilogram per Kelvin. And the temperature change, well, let's just assume it's the same as what it was before. So what was it before? Yeah, so 21.4 temperature change. So that's an assumption. The temperature change of the aluminium is the same as the temperature change of the water. Divided by, I had 1.24 grams of fuel. That was 46.069 grams per mole. All right, let's see if that's a big number, and that's part of the problem. $14. Well, I'm going to ignore the sig fig rules a little bit here. So that's just 14 or so kilojoules. Is that the big source of my error, that I didn't account for the aluminium? Oh, no, not at all. I had 675 and I was expecting 1367. No. So the aluminium, even though I did the maths on that, made a couple of assumptions, that's still not enough. I would say it's insignificant. Insignificant is a much better way of thinking about it in terms of the data problem that we've got here. Oh, I hope there isn't a mistake. I've checked, double checked, and triple checked, but I now throw this onto the mercy of the internet. Sometimes teachers complain that I do this because it makes the labs that the kids write up a little too easy. Okay, then you've got to change up your ideas as teachers. You've got to be flexible. And we're done.